Reminder, the critical point is an input value for which a function's derivative is undefined or for which its derivative equals 0. So f has a critical point any place f prime equals 0 or any place f prime is undefined. And the reason we started talking about critical points in the last section was because we were looking for extrema. So we talked about absolute extrema, we also call them global extrema. Those can occur at endpoints or at a place where there's also a relative extreme value. And those relative extreme values, those are tops of hills or bottoms of valleys. We said that, well, there's no way to draw one of those without drawing a place where the derivative is either undefined or 0. So here, these are all the different ways that I can draw relative extrema. Notice I have a horizontal tangent here. I have no slope there because the slope from the left and the slope from the right are different. Here I have a horizontal tangent. Here I have another undefined derivative. So, and we said that that was a big deal because now if I'm looking for extrema, I don't have to look at every possible x value. I only have to worry about finding, checking the output values at endpoints and critical points. So the first derivative test for local extrema. This is a big deal. Once you know this, you can probably answer just from this one rule another 5 or 6, maybe 7 questions on the AP test. So if a function, let's look at hill again. So think about that hill. Here, I know my derivative is 0 because I have a horizontal tangent. To the left of that spot, the curve was going uphill, which means the derivative must have been positive. Afterward, the function comes back downhill, which means the derivative must be negative. And what kind of extreme value is this? That's the top of a hill. That's a relative maximum. So the first derivative test has 3 parts. If f prime changes sign from positive to negative, that means if f prime was positive to the left of c and f prime is negative to the right of c, then f has a relative maximum at x equals c. This is relative maximum. Another name for that is local maximum. Relative maximum and local maximum mean the same thing. If instead f prime changes from negative to positive, that means f must have been going downhill and then come back uphill. Then I have a relative minimum. F can also have a critical point at which it does not change sign. So if f has a critical point c, but f does not change sign, f prime does not change sign at x equals c, then we have neither a relative minimum nor a relative maximum. So we talked at the end of the last section that just because a function has a critical point doesn't mean it has a relative extrema. But if it has a relative extrema, it definitely has a critical point. So let's see how you're going to see this on the test. Here we're asked to use the first derivative test to find relative extrema of this function, x cubed minus 12x minus 5. So we need to find the critical points of y so that we can mark them on our number line and find out what happens on either side of them, on the different intervals. So critical points, any place where the derivative is undefined or the derivative is 0. Well, x cubed minus 12x minus 5 is polynomial. It's smooth and continuous everywhere, so there's no place that the derivative will not exist. My only critical points are going to come from when y prime is equal to 0. So I'm going to find y prime, I'm going to set it equal to 0. That's my first step. 3x squared minus 12. So we're going to find the values that make y prime equal 0, and we're going to mark them on the number line to check out the intervals that those critical points break our number line up into. So when y prime is 0, 3x squared minus 12, I can divide everything through by 3. Get x squared minus 4 is 0. I'm going to factor, use the zero product property, and come up with two solutions. So this function has, y prime, has two zeros. When you make a number line to organize your thoughts, can I strongly suggest that you label it with the function name of the function whose sign you care about. So I care about, if I'm caring about the first derivative test to talk about where a function f is increasing or decreasing, then I'm interested in the sign of the derivative. So I've labeled this with y prime. So all of these interesting numbers that get marked on the number line, they're inputs to y prime, in this case that make y prime 0. And then we're going to be testing the sign of y prime. So I'm going to test a point to the left of -2 to figure out if this expression is positive or negative to the left of -2. All right, if you get to the place where you can do this with fewer steps, that's fine. I'm going to show my steps so you can kind of practice seeing this thought process for deciding whether these intervals on the number line are going to end up being positive or negative. So here's my function. Notice this is my derivative. I care about the sign of the derivative. I'm going to leave it in factored form. Now I'm going to pick a number to the left of -2. So let's call it -3. I'm going to replace all the x's with -3s. -3 plus 2, -3 minus 2. Now you might do that work in your head. It's fine, that's up to you. I'm going to ask myself now, if I have a -3 plus 2, is that a positive or negative? That simplifies to -1, which is negative. -3 minus 2 is also negative. If I multiply a negative number by a negative number, the result has to be positive. So since I was testing a number to the left of -2, I now know that any x value to the left of -2 that I use in my derivative is going to give me positive results for the derivative. So now I'm going to try a number in between -2 and 2. I'm going to use 0. So in my head, I think 0 plus 2 is positive. 0 minus 2 is -2, which is negative. And if I multiply a positive by, I'm going to say at x equals 0, this was x equals -3. A positive number times a negative number, the result is going to be negative. The number I was testing was 0, and that's on this interval between -2 and +2. And now I know that any number between -2 and +2 I use in my y prime, I'm going to get a negative result. I have one more interval to test. So I'm going to choose x equals +3 because that's to the right of +2. So if I let x equal 3, 3 plus 2, that's going to be a positive factor. 3 minus 2 will also be a positive factor. Positive times a positive makes positive. So now we have to get back to our original question. Where is y, the original y function, increasing? Where is it decreasing? I'll show you how to write up the answer on the next slide. All right, so I'm going to answer that y has a relative maximum at x equals -2 because, let me show you with a pen here. See how to the left of -2 I had positive derivative, to the right I had a negative derivative? That means that as you read from left to right, right here at -2, y prime changes from positive to negative. So I know y has a relative maximum at x equals -2 because y prime changes from positive to negative at that value. Similarly, the place where x equals 2, I was negative, and afterward the derivative is positive, so y prime has changed from negative to positive. So y has a relative minimum at x equals 2 because y prime changes from negative to positive. All right, so here's another example. We're going to use the first derivative test. Remember, relative extrema are relative minimums, relative maximums. And we can tell with the first derivative test about relative extrema by examining the first derivative, checking for where it changes sign. If it changes from positive to negative, I have a relative maximum. If the first derivative changes from negative to positive, I have a relative minimum. So here's my strategy. I have my y function. I need the critical point, so I'm going to find y prime and set it equal to 0. So notice I've used the product rule to take this derivative. So here I have my first derivative. This is not exactly polynomial, but my only technique for solving equations that have degree 2 and higher is to try to factor. So that's my technique. I notice both halves of my equation there, both halves of the right side, have a factor of e to the x. So I'm going to factor out e to the x. I'm going to collect together the rest and put it in descending exponent order. So I have a new equation. 0 is x squared plus 2x minus 3 all times e to the x. And I notice x squared plus 2x minus 3 factors. So that's my next step. I'm going to factor that. All right, so now that I'm here, I can use the zero product property. E to the x is never equal to 0. So that factor in my equation doesn't give me any solutions. But I have these two other factors that do, and I have two solutions. X equals negative 3 and x equals positive 1. So I'm going to mark them on a number line and test a point from each interval that the numbers on the number line break my number line up into. All right, so I'm going to test a point on each interval. I'm going to test a number less than negative 3. So imagine using negative 4. When x equals negative 4. Negative 4 plus 3 is negative 1, that's negative. Negative 4 minus 1 is negative 5, that is also negative. E to the negative 4 is still a positive number. We said e to the x is never negative. So it's going to be times a positive. But if I multiply a negative number by a negative number by a positive number, the result is going to be positive. What if I test x equals 0? 0 plus 3 is positive. 0 minus 1 is negative. E to the 0 is positive. If I multiply a positive times a negative times a positive, the result is negative. One more number to test. We'll test the number to the right of 1. What if I say x equals 2? It's going to be 2 plus 3 is 5. 2 minus 1 is 1, which is also positive. E to the 2 is also positive. So I'm going to end up with positive results to the right of negative 1. Now that I have my number line all filled in, notice I'm interested in the sign of y prime. So all those numbers I was testing them in y prime to see if y prime became positive or negative. So there's my conclusion. Now that I have my number line filled in, I can say that y prime changed from positive to negative at, that negative's missing, at x equals negative 3. So y has a relative maximum at x equals negative 3 because y prime changes from positive to negative there. And y has a relative minimum at 1, x equals 1, because y prime changes sign from negative to positive there.